Hi, yeah, this is Kayahan Saritas. I'm from Yale University, working as a postdoc in Sorab's group. So these are also the list of other our collaborators. I will be giving some introduction and basically talking about the method and the physics, and I will leave it to Kavitha, who is the person that did the heavy load on the Charm++ implementation. So as Glenn talked about a bit the electronic structure calculations. So our aim in here is to calculate or perform simulations of ions and electrons at the atomic level using quantum mechanics. So hence the Schrödinger equation. So this is inherently a many-body system. It's a many-body problem, but we assume that the ions are too slow, and then they are assumed to be frozen. So basically, you are interested in the interactions between multiple electrons. So this is a very hard problem to solve it exactly. So that's why we use approximations. And as Glenn mentioned, the DFT is a popular approximation for this to simulate the electron-electron interactions, which basically turns this problem into a one-muddy problem. That what you're doing here is basically showing all these electron-electron interactions into this VXC, which is the exchange correlation term in here. And so this basically becomes an eigenvalue problem that where you solve for the epsilon j's, which are the eigenvalues, and the psi j's are the eigenvectors of this differential equation. So there are various methods that you can use to get the same result, to perform electronic structure calculations, but all of them come with different accuracies and speeds and scalings. So the exact Schrödinger equation is is an NP hard problem, but the DFT method that we use is that has been used in the field routinely can simulate systems that are hundreds of atoms. But the GW method, which I will be talking more on, is able to simulate systems that are tens of atoms basically. So this is the scale of the systems that you can simulate using these two methods. So although both of the methods have similar scalings, the prefactors for these scalings are considerably different. And so being able to simulate hundreds of atoms with density functional theory makes it quite attractive in the materials science field to be used it basically hundreds or thousands different groups in the world. So, but there's one drawback with the density functional theory, and it is coming from the exchange correlation functional, which is used to simulate the electron-electron interactions. So the Kohn-Sham theorem that Glenn talked about is basically an exact theory with the condition that if you have the exact exchange correlation function. But if you don't know what the exact exchange correlation function should be, then there are basically plethora of different approximations, which may look like alien language to people outside the field. So, I mean, basically, if you're trying to simulate a brand new material where there is no experiments, then you have to cross your fingers to hope that your results should be good enough. The only thing that you can hope for is the relative energies or the qualitative agreement between different things that you're interested. So this what we are interested in the electronic structure calculation side is to get the right band gap So the band gap that, so we can define the band gap in this following way, because the band gap is essentially important for the optical properties of a material. So once you have the density functional theory expression like this and you solve for the epsilon j's and psi j's, basically the eigenstates, as we call it, are uh, put into this like ascending order, and then the electrons start populating those states. And once you reach this, the highest energy electron, and then if your system is insulating, then there's a separation between this epsilon n1 and epsilon n states, where like in this region you and no electrons are allowed to exist. So this defines your band gap. So basically, once you have an electron in here and you want to move this electron across the lattice, so that like you want that electron to conduct basically. So you need to excite this electron to this conduction band so that uh, you can, for example, like use it as a solar cell that uh, can help you like move electrons from one place to another so that you can generate useful like work from like a material like this. But the problem about the density functional theory is like coming from this issue, which is the derivative discontinuity. So the gap, so you can define the gap as the del E, which is the total energy versus the density. So this is a the exact physics of this term is telling you that this should be only piecewise continuous, like you can see in the red curve in here. But the DFT is often giving you this green curve, which is the local density approximation, as like one of the approximations in DFT, that you're always kind of underestimating this the E gap value in here. So that's why you need to use a method that can give you band gaps more accurately and more like reliable way. So we mentioned about this band gap, but why is this important? Essentially, this will tell you whether the material that you are interested in is metallic, semiconducting, or insulating. So you can do more fancy things about like getting the light matter interactions. And this also has a lot of engineering implications, being on the side of photovoltaics, lasers, or like luminescence of the materials. And if you look at the band gaps of these four different materials using different methods and the comparing those to experiments, basically what we are seeing again is that the DFT usually underestimates the band gap, but the GW is usually in a good agreement with the experimental values in here. But what are the challenges for the GW method? So it's memory intensive as a method, that it requires a lot of empty conduction bands, much larger than what you need for the density functional theory. So by that, it requires large and dense matrix multiplications, and the method itself, the naive implementation of the method requires order n to fourth scaling, which is unfavorable compared to the N-cube scaling of DFT. So what we want from here is the efficient and scalable GW software, and hopefully get it to like N-cube scaling so that we can be able to work with much larger systems in size, which were previously inaccessible to the GW method. So what are the main elements of GW method, and like what are the most expensive steps is, so we can summarize it using this diagram, but the main thing that we want to get is the inverse dielectric matrix, which is epsilon inverse in here. So from here, you can get the screened Coulomb interaction, and then you can get the dynamic self energy or like static self energy, depending on whether your energies are frequency dependent or not, so that these self energies can be used to determine the band gap of your material. But the most expensive part of a GW calculation is getting the polarizability matrix. So this can either be done in the G space or in the R space. That what we do in the, like practically people do in the field is that they typically get the energies and the wave functions from like, or you could say eigenvalues and the eigenvectors from DFT, which are often in the G space. Then you can convert this to R space using FFTs, which have this kind of scaling. And within the R space, you can calculate the polarizability matrix and then convert it back to G space using inverse FFTs. So why you have this like additional step of going FFTs and inverse FFTs is that what we find is that when you want to calculate the inverse dielectric matrix, so it can converge much faster, like using even decent small real space grids, so that it significantly saves on the like the costs by a factor of 2 in terms of the grid spaces. So there's that's why like this additional step is involved, but still you need to perform a lot of FFTs to get the wave functions in the R grid. So let's go back, and so we are saying here that the polarizability matrix is calculated with an order n to the fourth. But what can we do in order to reduce this order n to the fourth to n cube so that we can achieve better scaling? So what we can see in here, the operations here are basically matrix multiplications. And here what we can see is that in the polarizability, there is this term in the denominator, which is EC minus EV, which are the conduction and valence band energies. So these two terms are like together with the numerator. So what you want to achieve is that if you can come up with a form that is separable, so that this EC and EV are like can be like separated in from this expression, then you can uh, relieved you can be relieved from this quadratic interaction between those two terms, and then make it more into like the addition between the unoccupied and like occupied levels. So such that the main idea is finding a way to express this denominator in the separable form, such that this like quadratic term is reduced to a linear term. So what we do in that end, for that end, is to use the Laplace transform. And by using the Laplace transform on this denominator, uh, we get the EC and EV in the exponential terms, then which can be separated using this form. And this the integral for calculating this term can also be discretized using the Gauss-Laguerre quadrature, uh, basically where like you have the function as a like positions of the nodes and the weights of all the like nodes that you're interested in the Gauss-Laguerre quadrature. So in the final term, you get the n cube scaling, but you also have this nq term in front. But we are going to show in a bit that this nq is system independent, so it only comes as a prefactor to the n cube scaling. So rewriting the expressions in the previous page in here, we can see that we can achieve this separable form, that the valence and conduction band like calculations are obtained in this in this way. But what we see here is that a large number of NQ is needed to accurately integrate over the wide time domain made by the EVs and ECs in here. So what we can use for that end to use windows over ECs and EVs, so that we can minimize the range of the time domain, which is defined by the gap for that window and the bandwidth of that window. So the scaling between those two becomes closer to each other, so that the range of the time domain is reduced for every individual window that you're interested in. So the final step of getting the GW energies also involves the getting the self-energies, and for the dynamic self-energy, the expression in here that we have is quite similar to the polarizability, although some of the terms in the denominator are different. But we have mentioned that the separable form of the denominator is possible as long as you have an expression in this form, so that the same methods that we explained for the polarizability is also applicable for the dynamic self-energy. But what we are seeing for this case, because of the presence of this uh, frequency and the energies in here, what we know that this denominator can often, or like occasionally, can be zero, so that it requires a better treatment to be able to use it with the Gauss-Laguerre quadrature that we defined. So for that end, our group has developed a Hermite Gauss-Laguerre quadrature, which is similar to the Gauss-Laguerre quadrature, but has a different weighting function, so that it is better behaved around zero. So the final results that we have in here are for the gaps of silicon and magnesium oxide. So we have studied systems that are of the modest systems with 16 atoms. And the comparison that we do in here is the in-house versions of the N-cube and the N to the fourth codes. So we are seeing that the performance of the N-cube code depends on the accuracy of the quadrature. So the more points that you use in the quadrature, more accurately you calculate the integral. So that's why we are seeing multiple values for the band gap in here. And depending on how close you get to the N to the fourth result, the ratio of the computation, basically you are using more quadrature points, and then your requirements for the calculation is increasing. But if you can be more relaxed about the accuracy that you want, you can basically perform the same calculation with a much reduced cost, basically. So the similar results are obtained for both of the systems, that the performance improvement is close to order n, but much better performance is obtained using windowing, which is the red lines in here, that requires much smaller quadrature grids. And comparing the R code to the existing N to the 4 codes in the literature, what we see here is the Yamba code, which uses terminator. Basically, this is a method to eliminate the number of conduction bands, but while still being accurate, are relatively accurate. But this is still essentially order N to the fourth code. So what we see in here is that the performance of our code compared to that code is again nearly order n, considering the size of the system that we are interested. So the code is available in this address that is getting routine updates. And with that, I wanted to leave to Kavitha to give more updates on the uh, the OpenAtom implementations in the code.
Thank you.
So I'll just continue from Kayahan's presentation and talk about the OpenAtom GW P matrix and cube method computation that we recently implemented, and the parallel scaling results for the same. I'm a PhD student, Kavitha Chandrasekar, at UIUC, and this work is done with collaboration with the OpenAtom team. We have been working on the GWPSC parallelization for a bit now, and The primary computationally expensive phase is the p-matrix computation in R space that we had previously done in N-power 4 method, and now we have an N-cube method implementation, which is also complete in parallel. We also have other steps in the GW computation, which are smaller in terms of computation. They include the FFT of P into G space, inversion of the epsilon matrix, plasma and pole calculation, self-energy calculations. I'll primarily be speaking about the N-cube method in parallel. Um, the overall gist, we start with the charm++ implementation for p-matrix computation. Both the N-power 4 and N-cube method have a similar layout of the char arrays. We have the state vectors, which consist of both the occupied and the unoccupied state vectors, which are 1D char arrays. And then we have the p-matrix, which is a 2D decomposed char array. And the data is also 2D decomposed into tiles. So in terms of the input state vectors, it's a very straightforward implementation in terms of how the occupied and unoccupied states are stored in nodes. We currently have a node group which caches the occupied and unoccupied states as needed. So currently all the occupied and unoccupied states are broadcast to all the nodes, and only portions of the state vectors are used in the computation. So the computation of P matrix itself consists of primarily row and Rhobar matrix when it comes to the N-cube methodology. It uses a windowing technique, as Kayahan mentioned, which are smaller portions of the computation. So there's the outer loops that you can see in the pseudocode here, which consists of windows of occupied and unoccupied states. So primarily, the most computationally expensive part is computation of the row and Rhobar matrices. And then P matrix itself, as we can see, is formed by the element-wise multiply of the row and Rhobar matrix. So move on to the pseudocode for the computation of the row matrix. Primarily, it is done with the input occupied states. So we represent occupied states and unoccupied states with psi vectors. The number of occupied states is smaller, and we represent it here by L. So the total number of occupied states can be represented with a matrix or a 2D array of L cross N elements. So row matrix itself is computed by adding the elements of outer product of the occupied states. This is what we can see on the left side. So we have an outer loop consisting of all the occupied states, which is represented by L, and the row matrix is computed by the summation of the outer product of each of the occupied state vectors. So we can represent the same computation with a z-gem, as you can see on the right side. So primarily, row matrix is nothing but a matrix multiply of L cross N occupied states with the with another matrix L cross N transpose of the same set of occupied states. The computation of Rhobar is the next part of the computation. It's more expensive primarily because of the number of unoccupied states M, which is much greater than the number of occupied states. So this is essentially again the sum of outer product of the occupied states, and pretty much translates to a z-gem call of an M cross N and N cross M matrix of the unoccupied states, represented as Rhobar. Um, just a general pictorial representation of what I just mentioned. Right now, the occupied states are primarily L cross and N cross L by transposing it, and that's what we can see on the left side. This is a tiled implementation of P matrix. So we only have on each char we'll only have portions of occupied states that are read in, and only portions of the row matrix that are computed. Similarly, we have a tiled representation of the Rhobar matrix, which is computed with unoccupied states. Again, only portions of the unoccupied states are used in this computation. Um, but the overall size of the unoccupied state matrix multiply would be an n cross m into an m cross n matrix, resulting in an n cross n matrix of Rhobar. So finally, we have the output of n cross n matrices for row matrix and Rhobar matrix, and we perform an element-wise multiply of the uh, two matrices to obtain the final P matrix. Um, So in terms of performance of this method, we find that as expected, Encube is much faster than N power 4. And at the very least, we find that it's an order faster for the medium-sized data set that we use silicon 1 at 8 atoms. The output here for the N cross N is 20K cross 20K matrix. We find that it scales well on both Intel KNL and Intel Skylake nodes on Stampede 2. Um, and, uh, and in both cases, it's much faster and order faster than the NPAR4 method that we had previously computed. Um, our future goals here are to find the scaling for larger data sets as well, primarily the Silicon 432 atoms data set. I think. Any questions?
Thank you. So I'll take some questions here for either section of the talk. Because I have one. Have you had a chance to look at the weak scaling behavior?
So we're yet to do weak scaling. We're primarily looking to generate some data sets that we can use for weak scaling as well. But my guess would be that it would have good weak scaling, given the strong scaling also is pretty good.
Yeah, it's pretty good results.